Hello everyone, this is Sir Aris. Let us talk about introduction to groups. This is just a brief introduction. Let us consider four numbers, 1, -1, I, and -I. No matter what products and powers of them, so let's say 1 times -1, the answer is -1. So we find here -1, or 1 times I, or -1 times I, the answer is -I. Or let's say -1 squared, or -1 to the power of 3, or I squared, I to the power of 3, -I squared, -I to the power of 3, and so on. We never get any number besides this 4. So this property of a set of elements with a law of combination here, multiplication, when we multiply or when we take powers, the this we always get numbers that are members of this set. It's called closure property. Other similar sets include this e to the power of I pi over 2, e I pi, e3 I pi over 2, e2 I pi. Here, this is just equal to 1. Okay. And under multiplication, if we multiply them, we simply get back numbers, although some would exceed, say, greater than 2 or I2 pi, but in the complex plane, if it's greater than 2, the angle is greater than 2 pi, it goes back from 2 pi, it starts from 0 again, and then we count the angle from the x-axis or the horizontal axis. So it just goes back to, say, I pi over 2. Also, another example is 90-degree rotations of a vector. So suppose you have a vector. For simplicity, let's consider a horizontal vector. We rotate that 90 degrees, it becomes a vertical vector. Okay, another 90 degrees, this vector, and this vector another 90 degrees. So these 4 vectors, as long as we only do 90 degrees rotation, we'll go back to one of them, 90 degrees, or a multiple, integer multiple of 90 degrees. These numbers are the fourth root. So if you have 1, you take the fourth root, that's fourth root. The solutions are this or this. Actually, even this 90 degrees rotations, if you represent this with numbers, the numbers are complex numbers are this. They are all fourth root of 1. So we can write it like this. So a to the power of 4, take the fourth root. The answer is 1. A to the power of 3, a squared, and a. So this constitute a set, and this are examples of groups. So the different sets here, which are similar to this, they are examples of groups. More precisely, these different numbers that we've shown, or operations, are representations of the group known as the cyclic group. So if you have an element, you take powers, say a squared, a cubed, a to the power of 4. On the nth power, if it goes back to 1, it would be a cyclic group of order that power. Say 4 goes back to 1, so the order is 4. Precisely, or more accurate definition of a group is that a group is a set A, B, C, and so on of elements, which may be numbers, matrices, operations, for example, rotations, just like the rotations here, together with a law of combination. Could be a multiplication, addition, or successive applications of rotations or other operations. subject to the following four conditions. Closure, combination of any two elements is an element of the group. The law of combination or associative law, the law of combination satisfies the associative law here. Unit element, there is a unit element I with the property IA equals AI equals A. So I is the unit element. And that every element has an inverse in the group. For an element A, there's an element B such that AB or BA, they're both equal to the unit element I. Let us verify these four conditions for I minus I plus I minus I under multiplication. We've already shown earlier that this is closed under multiplication. Okay, plus 1 multiplied by this, you get the same. Let's say minus 1 times minus 1, that's 1. Minus 1 times I, that's negative I, which is this. Minus 1 times minus I, that's positive I. You take all possible combinations, you'll always get this one of these four numbers. So it is closed under multiplication. Associativity, it would be obvious that the associativity holds. You can verify that by taking all combinations, take the try the associativity property if it holds. Third, unit element. The unit element is 1. So the unit element is 1. Okay. 1 times 1 is 1. Negative 1 times 1 is negative 1. Plus I times 1 is I. Minus I times 1 is minus I. For the inverse, let's find the inverse. So for 1 multiplied by something, the answer should be 1. So that something is 1. Okay. Also, minus 1, multiply that by minus 1, the answer is 1. Plus I, multiply that with something, the result should be 1. That something is negative I. And lastly, negative I multiplied by I, positive I, the answer is 1. So all of them have, all of the elements have inverses, or each has an inverse. Say 1 has an inverse 1, negative 1 has an inverse negative 1, plus I has inverse minus I, and minus I has inverse I. So all elements have inverses. Each of them have its own inverse. So this set under multiplication is a group. Other definitions: the order of a finite group is the number of elements. When the elements of a group of order n are of this form, it's called cyclic, and is the cyclic group of order n here. Subgroup is a subset of the group, which is a group. So a subset, say among this a up to an, you choose, let's say, the first two. If that creates a group, then it's a subgroup. The whole group, so whole group is a subgroup. The unit element, say 1, is a subgroup because it is by itself a group. They are called trivial subgroups. So as always, there will be automatically two subgroups, the trivial subgroups, 1 and the whole group. Another or all other subgroups are called proper subgroups. In group theory, we typically use the term product or multiplication to refer not literally as the product or multiplication as what we are used to define defining product and multiplication, but it could be whatever operation we use for combining group elements. For example, if the group elements are rotation matrices, then we multiply the rotation matrices. But if the group elements are angles of rotation, we don't multiply the angles if we apply successive transformation using these angles, but we add them. So when we add, we simply add numerically the angles, but in group theory, we call that adding as still a product or a multiplication of two angles. So this product here is written in quotes because they don't really literally mean product, but a combination of group elements. For the set plus 1 minus 1 plus I minus I under ordinary multiplication, the group multiplication table is this. So I have rearranged it a little bit for some reason. So multiplication table, we simply multiply. Let's say 1 times 1 is 1, 1 times I is I, 1 times minus 1 is minus 1, 1 times minus I is minus I times 1 is I times I is minus 1, I times minus 1 is minus I times minus I is 1, and so on. So this would be negative 1, negative I, 1, I, negative I, 1, I, negative 1. Now another group is this set of angles under addition. This is a group. So the group multiplication table, it's a multiplication table, although we use addition. So 0 plus 0 is 0, 0 plus pi over 2, that's pi over 2. 0 plus pi is pi, 0 plus 3 pi over 2, that's 3 pi over 2. Pi over 2 plus 0, that's pi over 2. Pi over 2 plus pi over 2, that's pi. Pi over 2 plus pi, that's 3 pi over 2. And pi over 2 plus 3 pi over 2, that's 2 pi. But take note, 2 pi is 360 degrees or simply 0. It goes back to 0. We continue. This is pi. Pi plus pi over 2, that's 3 pi over 2. Pi plus pi, that's 2 pi. Again, that is 0. Pi plus 3 pi over 2, that'll be 5 pi over 2. But 5 pi over 2 is 2 pi plus pi over 2. 2 pi is 0. So the smaller angle from 0 would be pi over 2. Continue here. This is 3 pi over 2. 3 pi over 2 plus pi over 2, that's 2 pi, which is 0. 3 pi over 2 plus pi, just like this, that's pi over 2. 3 pi over 2 plus 3 pi over 2, that's 3 pi. 3 pi is 1 pi plus 2 pi. 2 pi is 0, so this is pi. So if you compare this with this table, take note that there's the ones are here 1, 1, 1, 1. Similarly here you have 0, 0, 0, 0. For I you have I, and I here. Same position for pi over 2, pi over 2, pi over 2, pi over 2, pi over 2. Negative 1, negative 1, negative 1, negative 1, and negative 1 here. That's similar in position with pi, 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 and pi. Lastly, minus I, minus I, minus I, minus I, minus I on this diagonal. Similarly, 3 pi over 2, 3 pi over 2, 3 pi over 2, 3 pi over 2. So the elements here in this multiplication table have a corresponding element here, and those corresponding elements have the same positions on anywhere in the multiplication table. So these two groups that have the same multiplication table are said to be isomorphic. So the multiplication tables are identical except for the names. So zero instead here we have zero, but here you have one, but the positions are the same. 0, 0, 0, 0, 1, 1, 1, 1, and all other elements. So these two 4-element groups are isomorphic to each other. They are really the same group. We simply name the elements differently. Now let us consider 3 identical atoms at the corners of an equilateral triangle in the xy plane with center of the triangle at the origin. So this is the origin. The transformations that keep the position of the triangle fixed, although we may interchange the atoms, form a group called the symmetry group of the equilateral triangle. So let's say we apply nothing. So that's identity or 0-degree rotation. That's one element. We can apply 120 degrees rotation. If we do that, this vertex or this atom goes here, the atom here goes here, the atom here goes here. But the position of the triangle is fixed. We can also do 240 degrees rotation. So this goes directly here. This one goes directly here, and this one goes directly here, or it's simply negative 120 degrees rotation. We can also apply reflection. Say we reflect along F, so these two atoms interchange, but the triangle is still the same. You do the same for G, you do the same for H, or reflection. The triangle is held fixed, although the positions of the atoms may interchange. So these are the 6 elements of the symmetry group of the equilateral triangle. They can be represented just like the 2 isomorphic groups here. So we can represent this by different numbers. So for example, the identity, we can represent it by a matrix. So say, let's call the matrix I. I is just the identity matrix 1, 0, 0, 1. For rotation, let's call that A. This would be 120 degrees rotation, negative 1/2, negative square root of 3 over 2, square root of 3 over 2, negative 1/2. So just like rotation matrices. We can call 240 degrees rotation by B. So this is negative 1/2, square root of 3 over 2, square root of 3 over 2, negative 1/2. For reflection, let's call the reflection along F. Okay. So it look like the matrix would look like 1, 0, 0, 1. Through G, let's call it G. G would be 1/2 minus square root of 3 over 2 minus square root of 3 over 2 and negative 1/2. And lastly, for H, you have 1/2 square root of 3 over 2 square root of 3 over 2 and negative 1/2. So these are the matrix representations of the symmetry elements, which are transformations. You can multiply these matrices to create the multiplication table, or say you can also look at this, for example, A times B. The answer should be always I. A times A, that should be equal to B. Okay. B times B would be equal to A. So if we check that here, A times A, that's B. B times B, that's A, and so on. Now take note that G times F, that's A right here. But F times G is B. They are not different. They are not the same. This because matrices don't always commute. When you multiply two matrices, you switch the position, the answer may not be the same. So they don't follow the commutativity, or they don't commutativity property. In group theory, if every two group elements commute, then the group is called abelian. So in this case, the symmetry group of the equilateral triangle is not abelian or non-abelian. Other properties, two group elements A and B are called conjugate if there is a group element C such that C inverse A, C equals B. If we let C run through all group elements, say we take C to be all of the group elements, and then we find all group elements conjugate to A. So if we find B for all values of C, this set is called a class. It's not necessarily a group. It is it would be a subset of the group, but it's not a group. It's not a subgroup. The trace of a matrix is called its character. It can be shown that all matrices of a class have the same character. So since we can write matrices in infinitely many ways, to say we rotate the reference axis using similarity transformation, just like what we did in the previous section. But since similarity transformations, you can show that they do not change the trace or the character, then the character associated with the class is independent of the choice of the coordinate system. So whatever coordinate system you choose, the trace, when you solve for the trace or the character, it's always the same for a certain class. Now for matrix or for any group element representation, it's reducible if all of the group matrices can be diagonalized. So we apply diagonalization. You take the eigenvalues. The eigenvalues would be the elements on the diagonal. If all of the group matrices, when diagonalized, use the same unitary transformation, then they are reducible. But on the other hand, if the set of matrices cannot be simultaneously diagonalized, then it's called an irreducible representation. We also have infinite groups. So these are groups that have infinite order or number of elements. Say the set of all integers, including positive, negative, and zero, under addition is a group. But under multiplication, it's not a group because zero has no inverse. So we need something when multiplied to zero, the answer is 1, but that doesn't exist, or that is undefined. Under ordinary multiplication, the set of all rational numbers except 0 is a group. Actually, for here, it may still not be a group. So for rational numbers, because here, for example, the number 3, the number we need to multiply to 3 to get 1 is 1 over 3, which is not an integer. So we need rational numbers except 0 under multiplication to make it a group. Subtraction or division cannot be group operations because they don't satisfy the associativity law. For example, x minus y minus z does not equal to x minus y minus z. Okay, because this minus here should already become positive, and that would not be subtraction operation anymore. Same with division. For division, it doesn't follow associativity. So the set of all orthogonal 2 by 2 matrices under matrix multiplication is called O2. Okay, orthogonal two-dimensional matrices. If the matrices are rotation matrices, so they have the determinant +1. The set is a group called SO2. S stands for special. The set of all unitary n by n matrices are called UN. It's a group under matrix multiplication. The subgroup SUN, S is again special. If they have determinant +1, it is also a group.